Discussing the basics of dust collection system design for woodworking. My name is John Daniel. I lead our corporate efforts in supporting our engineering firms around the world here at Donaldson Company. We also have Amy Miller with us today, who's our training manager. She'll be working behind the scenes and will be moderating the Q&A session at the end.
All right, hello. Thanks everyone for joining us today. As you think of questions throughout the seminar or throughout the webinar, please feel free to just chat them in as you think of them, and we will address them all at a Q&A session at the very end.
We're going to start off today's webinar by reviewing some common woodworking processes where dust collection is usually needed. Then we'll get into the four primary components of dust system design: hoods, ducts, collectors, and fans. We'll finish up at the end with the Q&A session. Please note it can take years of education and experience to become an expert in dust collection system design. The goal of this session is just to give you an overview of the basics. If anybody isn't familiar with Donaldson Company, we've been solving complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. We pride ourselves on having a global reach with a local touch. Our world headquarters is in Bloomington, Minnesota, and we have 55 manufacturing plants and 21 distribution centers around the world. Before I introduce our featured speakers, I want to quickly explain how to engage with us. As Amy mentioned, please chat in questions into the chat box, and we'll be addressing them at the Q&A towards the end of the session. And during the webinar, you may be asked a question or two. You can respond by a thumbs up or thumbs down by clicking the face icon at the bottom of the screen.
All right, we're glad to be here today. To start off, we'd like to take a quick poll to find out the level of experience for our attendees today. So if you would just kind of chime in there with A through E there, indicating your experience level from none to experienced.
Well, it looks like we have some A's, some B's, some C's, so it's a pretty wide range. Lots of them coming in. Covering the spectrum, Jason.
Ah, very good. And that's what we like to see, and that kind of helps us as we go through the presentation here. So let's get started. Let's talk a little bit about the dust generated during the woodworking applications and the processes that create them. So there's a lot of important reasons to control dust generated in woodworking, such as improving the overall air quality for the employees, exposure control. We want to minimize any dust in the breathing zones of the operators and other employees in the area. Hood design can play a big role here. There's environmental concerns, which frequently fall under EPA standards. Safety concerns, such as NFPA guidelines, cleanliness of the facility. In some of our larger applications, we have operations that remove over a tractor trailer full of dust in a day. So you can imagine what that would look like if we just let it pile up. And lastly, there is machine functionality and performance to consider. So there's many different types of woodworking industries, and we typically break these down into two main categories: raw materials and finished products. Raw materials include dimensional lumber and rough mill, engineered wood products such as OSB, plywood, MDF, and so forth, and rough sawmills. Whereas finished products are going to include kitchen cabinets, furniture, millwork, and other finished products. The type of raw material is another important consideration in selection and sizing of dust collectors. We break these down into three primary groups: softwoods, hardwoods, and engineered lumber. Softwoods typically have a much higher moisture content, and frequently when working with pine, we would move to like a polypropylene bag as an example of something we might do to compensate for the higher moisture. Hardwoods are used more in finished products like furniture and cabinets, but different species of hardwoods can produce very different dust characteristics, even coming off the same operation. And then there's engineered lumber, which is often used in construction. All right, the map shown here, or diagram shown here, shows several different dust collectors in use. We have our large bag houses kind of shown at the center of the map near the bottom, as well as one outside near the outside wall and the ship. We see a small cyclone in the upper left corner of the building, and we see an example of an enclosureless collector toward the right-hand side of the map. Now we'll take a look at some common woodworking processes that utilize dust collection. Joining is a flattening of one face and one edge as part of a milling process. Planing is used to smooth and remove excess material from wooden surfaces to create a near finished surface. Both of these processes can produce a large volume of dust and much larger particulate. Most people are quite familiar with sawing and cutting. Now there's many different types of saws. You have circular saws, band saws, table saws, miter saws, and so forth down the line. And many of these saws are hooded in quite different ways. Drilling and boring. Drilling is obviously creating a hole in the wood, whereas boring is removing material around a pre-existing hole. Both of these can be challenging for dust collection due to the depth of the hole being produced and the difficulty in getting the suction to the point where it is needed. Routing, shaping, and molding all involve putting a profile onto a wood component. They can be complicated and automated, or simple like a hand router you might use in your home wood shop. Many of the CNC routers require you to overcome a large amount of static pressure. Lathe turning is the art of shaping wood into cylindrical shapes, such as chair legs and spindles. One of the fun ones we did involving dust collection on a lathe is at Louisville Slugger, where bats are turned on a lathe. An interesting side note regarding Louisville Slugger is that the bats used to be nearly 100% ash, and they are now mostly all maple. This change in species had an impact on the dust collection system. You get far more curls and strands with the maple than you did with the ash. Sanding is a process of taking away material to create an ultimate finished component and then adding finishes like stains or paints. The right-hand picture shows a multi-edge sander. The left-hand picture shows a belt sander. It also shows really poor ductwork. A Donaldson design system would look a lot different, but this is representative of what many shops look like when we first enter them. As you can see in woodworking, there are many processes and machines that create dust. At Donaldson, we break the dust down into 3 basic categories based on the dust characteristics. These categories will help in our selection and size and style of filtration device. We define Class 1 as light or fine dust, such as dust generated from sanding. Class 2 is a medium size, such as dust generated from saws, routers, and joiners. And 3 would be your larger size dust, such as that generated from planers and lathes. In addition to the size of the dust generated, there are a few other factors that we take into consideration to help select and size a dust collection system. We already spoke briefly about the different wood species and types. Moisture content can be a very important consideration. Are there glues and resins present that can create a challenge? What type of equipment or process is producing the dust? What are the airflow and static requirements of the machine? Is the process continuous or intermittent? How much dust will we be collecting? A 5-gallon pail or a full tractor trailer? What are we going to do with the collected dust? Will we drop it directly into a drum or bag, or will we convey it to a storage hopper? We want to look at the total cost of ownership, and last but certainly not least, we want to consider combustibility. The wood dust generated during the manufacturing process may be, and most likely is, combustible and poses a fire, flash fire, or explosion risk. I'm sure most of you are familiar with the fire triangle shown here. Fuel, oxygen, and a source of ignition produce fire. When the source of fuel, which in our case is the dust we're collecting, is finally dispersed, it can lead to flash fires. When that dust is then contained with a dust collector enclosure, the conditions are right for a dust explosion. We are going to circle back to this towards the end of the session, but it's a complex and complicated topic. Toby, do you want to start talking about system design?
Hey, Jason, thanks. Let's talk about the basics of dust collection systems for woodworking. Here's a diagram of a typical dust collection system. You have a blower or a fan, creates an airflow which is used to capture dirty air with the hood and then convey the material through a series of ducts to the dust collector. Here the contaminant is separated out as clean air passes through the filter media to the fan where it's discharged to the atmosphere. These systems are some of individual parts that are designed based on the characteristics of the dust and various application factors. If one component's poorly designed, the whole system's affected. In system design, we have two main objectives. We want to accurately predict the volume of air in CFM that's required to effectively capture and control contaminants at their point of generation. We also want to predict the total energy and horsepower required to produce those required airflows. The publication shown here is the Industrial Ventilation Guide. It is an important resource for proper system design. The vent manual is written by the American Conference of Governmental Industrial Hygienists, or the ACGIH. This is a nonprofit scientific organization that advances occupational health and environmental health. They offer multiple courses throughout the year on system design using the Vent Guide as a textbook. I've been to the ventilation conference and attended a couple courses or several courses to develop my design expertise. And we also have a few experts here at Donaldson that are instructors at the conference. If you have any interest in developing your system design knowledge, I would highly recommend both of these resources. The ACGIH guidelines are considered by most in the industry, including OSHA, as the standard for proper ventilation design. There are a lot of different formulas that we use in the design system. The most basic and widely applied is airflow. We refer to it as Q equals V times A. The Q is the total CFM of air needed. In order to get the Q, we multiply the velocity of air, which is the V, by the area of the hood or the duct that the air is flowing through. The formula is one of the basic building blocks in designing dust collection systems. We start with the pickup points and calculate using the formula to get the required airflow at each pickup. This will give us the total CFM needed for the system. This formula is also used when we're calculating the required velocity within the duct. So throughout the design of the system, we'll refer to Q equals V times A over and over and over. The first component that we'll talk about is the hood. This is a critical component for system design that will allow the containment and collection of the dust. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it's released, while minimizing the energy required to do that. When it comes to assessing existing systems, few common mistakes we see are wrong hood style being used, the hood's not located in an effective position, or you have inadequate airflow at the hood. You can see in this picture, the manufacturer provided a hood the full length of the sanding belt, which is great. However, the 90-degree elbow immediately above the hood that you can see in the photo is not ideal. The most common hood style used in woodworking system is a closed capturing hood. It relies on establishing a general flow pattern in the hood opening to produce a capture velocity at a specific distance from the hood. There are four main types of capturing hoods. On the slide, they are in order from least to most efficient and also in order from least to most expensive. So you have a raw edge hood, flanged hood, tapered hood, and then a bell mouth hood. So regardless of the hood style, to be an effective hood, it must be positioned properly relative to the point where the contaminant is emitted. Remember, the first objective in hood design is to minimize the air volume required to maintain capture efficiency. To minimize air volume, the hood must be close to the capture point without disrupting the process. Hoods simply just can't reach out and control contaminants far from the inlet. So think about your vacuum at home. To pick up debris from the floor, the vacuum head must be close to the contaminant or just doesn't have any effect. The hood positioned twice the distance from a contaminant emission point rather than at the capture point, we'll need to draw approximately 4 times more air to produce the same capture efficiency. So the more air means larger equipment, larger ducts, larger fan with higher horsepower, and all of which add increased capital and operational costs. When determining airflow at the hood, the main design factor is called capture velocity, the velocity required at the point where contaminant is generated and gains control of the contaminant and directs it into the hood. For wood dust, capture velocity is typically between 150 to 750 feet per minute, or FPM is what we refer to that, although it's going to depend on the application and the style of the hood that you're going to use. So when you're designing hoods, we want to avoid airflow extremes. Too much airflow at the hood or pickup point may mean you're picking up good product rather than just nuisance dust. It also can increase your risk of capturing unwanted particulate like sparks or embers. And since more energy is required to move more airflow, it could lead to higher than expected operational cost. Insufficient airflow at the hood could require additional housekeeping measures to be implemented. Depending on the dust, it may lead to increased risk of exposure. Once we design the proper hood to capture the contaminant, the goal is to move the particulate to the filtration system through a series of ducts.
Sorry to interrupt you, Kobe. Just wanted to remind everybody to chat in your questions as you think of them, and Kobe and Jason will address them towards the end of the session.
Thanks, John. Properly designed duct system should pull the minimum airflow required at each hood, as well as maintain velocities required to transport material through the duct into the collector. And you have to be able to do this utilizing the least amount of energy as possible, minimizing any wear and tear on the duct components. So a few common mistakes that we see when it comes to duct design: incorrect ducting being used, incorrect duct size or fittings being used, and the duct system's just not balanced correctly. The minimum duct velocity is a critical design factor. The lowest velocity, where all contaminant will remain suspended in the airstream, is what we refer to as duct velocity. If you go below this velocity, dust could settle out within the ducts and cause other safety issues. Duct work, no matter the size, must be full of air at the design conveying velocity to avoid any settling out. Here you can see a list of different types of dust and their recommended transport velocities on the slide. For many of the light dust generated in woodworking, like sanding, the industrial ventilation manual lists the minimum velocity is 2,500 to 3,000 feet per minute. However, 4,000 feet per minute duct velocity is for combustible dust, which is typically what will be in woodworking. So you're going to see duct velocities in that 4,000 to 4,500 feet per minute range. If the duct velocity is too high, it's going to require more energy to move the air through the duct. Ultimately can impact the size of the system, as well as create issues such as noise, abrasion, wear and tear on the duct, and other equipment. A few pieces of advice when it comes to duct type. Rectangular duct is commonly used in HVAC applications where you're going to be moving air only. We don't want to use that in industrial applications because dust settles out in the corners. It's okay to use it on the clean air side though. When specifying industrial duct systems, make sure you call out round, heavy-duty industrial duct work. Most dust collection applications will use class 2, 3, or 4 ductwork, which are designed to SMACNA standards. Typically, the higher duct class rating of the ductwork, the higher the gauge. Spiral duct tends to leak air. It can impact your design airflow by about 10%. And if it's used outside, it also could provide a prime source for water to enter the ductwork and get into your dust collection system. So spiral duct is generally not recommended. Flexible duct's popular because it allows operators to move the hood locations to fit their process. However, that comes at a price because there isn't smooth inner surface inside the duct. When the air moves through it, it creates a ton of turbulence and therefore requires significantly more energy than traditional hard ducting. So if you're going to use flexible ducting, we recommend minimizing that as much as possible. Speaking of flexible duct, we found this fantastic video showing what not to do. Some flex duct may be required as the machines are moving, but there's way too much in this process. It's going to lead to higher static pressure, lower airflow, which all leads to material buildup in the ductwork. I'm sure it wasn't designed this way, but somebody added flex duct along the way. So if your customer's facility looks like this, give us a call. We can help you. And my last piece of advice about ductwork, avoid T's and 90-degree angles. If your elbows are mitered 90-degree turns, all the air has to slow down, turn, then speed back up. Same with branch fittings. A T fitting creates a ton of turbulence as the air is coming in at a 90-degree angle, and the turbulence equals more energy consumption or a higher static pressure. So if you're designing a system, it's important to select options that minimize the turbulence within the duct and avoid things like T's and mitered 90s. If you're using 90s, we prefer it to be long radius. I mentioned earlier that having an unbalanced system is something that can go wrong with the duct design. When customers add new equipment to an existing system, they often don't consider the impact it has on other existing equipment. So in most cases, existing systems aren't modified to accommodate the additional airflow or static, and it becomes unbalanced. Luckily, if you know the customer is going to be expanding the process, there's a few ways to design future lines into the system so they don't have to sacrifice the performance. Having a balanced system is one of the most important aspects to an effective dust collection system. So it ensures you're pulling the correct amount of air from each hood. A lot of issues have been created in existing systems where the process owner goes and adds additional pickup points, doesn't account for the ramifications downstream. So give us a thumbs up if you ever seen this in your experience. You design a system, you find out later the process owner changed something.
It looks like we're seeing a bunch of both thumbs up and thumbs down. So people are certainly running into this this scenario. Chloe?
Sure, I see this quite often. What about you, Jason?
All the time. Yeah. Most of the time, these additions were not planned and the system can become unbalanced. If you know a customer is going to be expanding their process, there are ways to design future lines into a system so they don't have to sacrifice performance. But if a customer needs to add a line to an existing system, call in a professional to help. Don't just do it and expect the system to work. Our next system component is the dust collector itself. The main objective of a dust collector is to filter or remove the dust from the airstream and discharge the collected dust into a container or takeaway system. The objective is to do this as efficiently and economically as possible while operating in a stable and predictable fashion. The most common mistakes or things we could do wrong that we see when it comes to collector design are the wrong filtration technology, like using a cartridge when a baghouse would be more effective, incorrect sizing of a collector, either too aggressive or too conservative, or poor installation or system design, such as poor duct design or inlet orientations. The photo here shows a series of 3 of our RF collectors sitting on a common platform. Over my career, I've used many different dust collector types on woodworking applications. When applied to the appropriate operation, they can all be successful, but put the wrong collector on the wrong application and you can quickly get in trouble. Cartridge collectors, cyclones, and enclosureless collectors all have their place, but baghouses are the most common collectors used in woodworking. Our baghouses are broken down into 3 different cleaning types: low pressure cleaning, medium pressure cleaning, and high pressure cleaning. The high pressure cleaning would be a compressed air system that reverse pulse jets the unit. Enclosureless collectors are limited to no more than 5,000 CFM by NFPA. The RF collector is a workhorse in the woodworking industry. It can handle large air volumes and large volumes of dust. It has a cyclonic inlet that provides some pre-separation prior to reaching the filters. The bags are cleaned with a medium pressure produced by a positive displacement blower, thus saving you on expensive compressed air. The RF also has a single inlet, single outlet, and single dust discharge point. The RF helps with a quick and easy installation due to the fully welded construction. Units are usually lifted off the truck with a crane and set into place. The photo here shows an RF collector. The fan is mounted on the left side of the collector and is connected with the large galvanized duct. You can also see a pulse jet baghouse in the background. The RP collector is very similar to the RF and has a lot of the same features, but the RP uses pleated filter bags rather than the fabric bags over cages. The pleated bags are shorter than fabric bags and they have more square footage of media per filter. The pleated bags can work very well in applications where a high percentage of the dust is sanding fines and applications where there are concerns about interstitial velocity. The picture here shows a modular bag house. The modular bag house is a high pressure cleaning system or pulse jet cleaning system that fires compressed air back through the filters to clean them. The MB comes in square and rectangular configurations and are typically used for low and medium volume applications. Pulse jet bag houses can take up a good bit of real estate, and they can also have multiple inlets, outlets, and dust discharge points. They do, however, typically have lower capital costs than other bag houses. Sometimes a traditional bag house isn't going to be the best option, and we need to use a specialty collector. The Dalomatic G2 is a great selection if we are dealing with agglomerative or sticky dust. These collectors have envelope-shaped bags that have a tremendous snapping action during pulsing, shown in the graphic on the left. The snapping action aids in dislodging the dust cake. The Dalomatic also has a downward airflow pattern, which helps with getting light fine dust down into the hopper and out of the collector. It is a pulse jet collector, so it will use plant compressed air. Baghouse collectors use bag filters. The two main types are fabric and pleated. Fabric bags are installed over metal cages. During filter changeout, the entire bag and cage are removed from the collector. The used fabric bag is removed from the cage and new bag installed in its place. Then the cage with the new bag is put back into the collector. Many bag houses can have several hundred bags, so the process can be very time-consuming and dirty. Pleated bags are a one-piece design. They tend to be shorter in length and take significantly less time to change out. Not all bag houses can use pleated bags, but they are a great option for certain applications. When I'm designing a system, the very last thing that we do after completing all the static and airflow calculations is select and size the fan. Toby, do you want to talk about fan design?
Absolutely. The fan is like the heart of a dust collection system. So it has two job responsibilities. First, a fan must deliver the necessary volumetric flow at the required static pressure to drive the operation of the system. And since many dust collectors can operate with dirty and clean filters, they require airflow. The required airflow is often has to be maintained over a range of static pressures. Secondly, the fan you select should be able to deliver the desired static and airflow with an accurate energy efficiency at an acceptable sound level. So, for example, non-material handling fans located on the clean side of a collector are more efficient than a material handling fan on the dirty side of the collector. Fan challenges generally fall into two categories. It's a poor fan selection or a poor fan installation. A critical component of fan design is static pressure. It's basically resistance that the airflow must overcome due to system components. It's expressed in inches of water gauge. When we design a system, we calculate the total static pressure so that we can size the fan appropriately. Here's an example from a recent system that I designed. We had hoods that totaled of 1.5 inches of water gauge. The ductwork, including straight runs of duct, elbows, branch entries, that all totaled 2.5 inches. The filters in the collector, when dirty, totaled 6 inches. So the total system static pressure for this particular project was around 11 inches. Fans are sized based on a system's total static pressure and the required airflow. So let's say I need to size the fan for the example I just gave you. 11 inches of water gauge and the airflow is 9,000 CFM. We use the system static pressure of 11 inches, then line it up with the airflow of 9,000 CFM. Then we line those factors up and we land in between a torque backward inclined or TBI 25 and TBI 30. So we go to the curve of the right where we land. Since it's rare, we land right on the curve. So in this case, I would have selected a TBI 30. To finish things up, and then we'll open up for some questions, there are a few other design considerations that we want to think about. Total cost of the ownership. So some things to consider would be how much energy is required to operate it, where's the unit coming from, how easy is it to get parts, how long do the filters last, how easy is it to change out filters or maintain the system, and what is the life expectancy of the system. Another consideration I want to mention is how technology is being used to monitor dust collection systems. We have smart technology all around us these days, from our TVs to our toasters. Donaldson's developed a device called IQ to make dust collectors smart. This device gathers important process data in real time, creates automated alerts, has historical reports, and it's available to customers at no charge. It's a great way for process owners to manage and track regulatory compliance information and troubleshoot dust collection issues more efficiently. And regulatory considerations, everyone's favorite, right? Each of these agencies must have design expectations to reduce process-related hazards, and as we all know, they aren't always consistent with each other. Knowing the hazards related to the process the system is designed to handle, this will allow you and the customer to make some critical design decisions up front in the process. It can be very expensive and time-consuming to change the design once the equipment is installed and in operation, so you want to try and be out in front of it as much as you can. I want to talk briefly about National Fire Protection Agency, or the NFPA. It's a global self-funded nonprofit organization devoted to eliminating death, injury, property, and economic loss due to fire, electrical, and related hazards. Standards developed by the NFPA are called consensus standards because they're widely recognized by authorities. NFPA standards are referenced in national and international fire and mechanical codes, and they are adopted by many states. The local building inspectors and fire marshals may be required to enforce NFPA standards. OSHA also considers NFPA standards to be good engineering practices, and during general safety inspections may reference NFPA standards when issuing fines to a facility under the general duty clause. Here's a list of the current industry-specific NFPA standards. NFPA 664 provides information to help identify and manage fire, flash fire, and explosion hazards associated with combustible dust and particulate solids found in wood and wood processing industries. Specifically, it addresses the prevention and protection requirements for industrial, commercial, and institutional facilities that process wood or manufacture wood products. This is a recent job. We did a school shop in Wisconsin. This is actually a small cartridge collector. Since the airflow was pretty low at 4,500 CFM, we didn't need a baghouse. We could go with the more economical, smaller size cartridge collector. The dust was combustible, and as part of the mitigation strategy, they went with inlet isolation, high-speed abort gate, an explosion vent, and dust discharge isolation. In the photo, you can see our small DFE collector with the explosion vent on the side where the white rectangle is. You may notice underneath the hopper, we have an NFPA-approved rotary valve. And in the left of the picture, in the duct runs, you can see the inlet isolation valve as well as the high-speed abort gate. For those of you that are new to dust collection, just know that combustible dust is important, complicated, and ever-changing. If you have any questions, please reach out. We have combustible dust experts on our team that can help, and that goes for the entire system, not just combustible dust mitigation. Designing dust collection systems for woodworking can be complicated, and there's a lot that goes into it, but that's what we're here for. We've sold countless dust collection systems around the world. We have local support in your market, and we are always here to help.
Thank you. Great job, guys. We're going to